Hi, welcome to the video on balancing nuclear equations. So in this video, I'm going to go over how to balance nuclear equations. Now, when we talk about balancing nuclear equations, it's based on something known as the law of conservation of either mass, matter, or energy. And that law states that matter, mass, and energy cannot be created nor destroyed. And the reason why matter, mass, and energy are all sort of together is because energy and mass are related by E equals mc squared equation. But anyway, the idea is that you cannot create or destroy matter, mass, or energy, but you can change it around a bit, transfer it. So in terms of balancing nuclear equations, when we say we're balancing them, what that means, what that translates to, is that the sums of the atomic and mass numbers must be the same on both sides of the equation. So this is called an equation. Sort of like in math, the equations are separated, the left and right side are separated by an arrow. And the left side tells you what you're starting off with. So these two things, aluminum 27, helium 4, they're what you start off with. They're like your ingredients. You combine them together and they make this phosphorus 30 and this neutron. The other thing to note here is when balancing, notice we have a neutron. There are some symbols that you need to become familiar with. Essentially, if you see something with a 0 in the where the atomic number should be, that is or a +1 or a -1, or even a 2, because an alpha particle is equivalent to a helium-4 nucleus. You should check here, because you're not going to find it on the periodic table. All right, so let's go ahead and get into how we balance it. I'm going to do these two, show you how these two were done. These are the examples that are already done for you, just to give you a sense what you ought to be doing. So when balancing, as we said, we want the mass number, which are the numbers on top, the total, on both sides of the arrow to be the same. Now in this problem, I didn't have that blank filled in, so I had to figure out what goes there. So how would I do that? First thing, I would take the side that's complete, where there are no blanks, and I would add up their mass numbers, 27 plus 4. That's going to give me a total mass number of 31. So 27 plus 4. And then you do the same thing for the atomic numbers, because that also must be the same on both sides. So 12 plus 2 gives me a total atomic number of 14. So now what I want to do on this side is I want to, actually there's a mistake here. Let me go ahead and correct that. Aluminum has an atomic number of 13, sorry, not 12. So let's correct that. And to prove that to you, we can look on our periodic table. There you go. Aluminum has an atomic number of 13. All right, so now this is looking good. All right, great. So I have my total mass numbers on the left side and total atomic numbers on the left side all done. So now what I'm going to do is I will need to figure out, well, if there was a blank here, what numbers would I need for my mass and atomic number in order for both sides to be the same? So if we take a look at what we already had, we had a 30 and we had a 15. So let's start with that 30. I asked myself, 30 plus what will give me 31? And the answer to that would be a 1. So that's how I know that the mass number of my unknown was a 1. And then I asked myself for the bottom here, for the atomic number, I have a total of 15 on this side. So, and on the right side, I also have 15. So 15 plus what will give me 15? Well, that would be 0. Okay? So now I'm looking at these two numbers, and these numbers are now going to help me identify what my unknown is. So I have a mass number of 1 and atomic number of 0. Now if you try to go by using the atomic number and you look on the periodic table, of course, there's nothing on the periodic table that has atomic number of 0. So that's your clue that you need to use one of these fancy symbols here. And the answer to that is a neutron. So you find the one that has a 1 and a 0, and that's a neutron. Now let's take a moment to explain why this is a neutron. Remember, the mass number represents the mass of the atom, or it could be a particle. And the bottom number represents the number of protons. Now remember, protons are the only thing inside of the nucleus that has a charge. They have a +1 charge. So if we look at that bottom number, that's actually kind of telling you the charge inside of the nucleus. Now we know neutrons don't have a charge. So that's the reason why the bottom number here is 0 for the neutron, and the top number here is 1 for the neutron. Neutrons have a mass of 1, but no charge. So when we're dealing with these particles, the top number is still the mass number, because it represents the mass. But the bottom number, oftentimes they call it the nuclear charge. Let's take a look at some of the other particles as well. A beta particle is like an electron. Now we know electrons have essentially no mass, but they have a -1 charge. And so that's why this symbol here, you have a 0 for the mass number because electrons have no mass, and a -1 for the charge since electrons have a -1 charge. Something like a positron, which is sort of like the opposite of an electron. So a positron has no mass, but it has a +1 charge. And this is just a special particle that comes up in nuclear chemistry. Some other particles we have here, gamma rays, they have no mass and no charge. This is just essentially a photon of high energy. And of course you have your proton, which a proton is equivalent to a hydrogen-1 nucleus, because in a hydrogen-1 nucleus you only have a single proton. So at any rate, this is sort of what this, you would use these to identify your particle if the atomic number, also known as the nuclear charge number, is 0. All right, you see some of them have zeros, or if you see a -1 or a +1, come up here and look to figure out what the symbol is. Okay, let's get back down to balancing. Last one we'll do together. So we're going to do the same thing again. We want to make sure, in order to figure out what would go in the blank, we want to make sure that we correctly add the total number for our mass number and the total atomic number on the side that's complete. We're going to start there. So the left side, once again, is complete. It could be the right side that's complete, but in this case, it's the left side again. So I start with the mass number, 63 plus 2. That's going to give me 65. As my mass number for my atomic number, 29 plus 1 will give me 30. I just get my total. Now I'm going to try and figure out, well, when I add what's given here, will give me that same total. Remember, this is our blank. I'm going to put this total on the other side just so that we can see it. So on this side, we should also have total mass number 65 and a total atomic number of 30. Now, if you look at what we're given 2 neutrons, okay? That number in front, the coefficient, just like in math, the big number in front is the coefficient. It's telling you have 2 of them. So that means that when I do this math, when I try and figure out what goes here, I have to take into account that there's not just 1 neutron, but 2 of them. So now I'm asking myself, well, 2 times 1, which is 2. So right now I have a mass number of 2. 2 plus what will give me 65? And the answer to that, of course, is 63. That's how I got that top number. So once again, I had 2 neutrons here because there's a coefficient in front. So that's 2 times the mass number, so 2 times 1. Right now my total mass number is a 2. So 2 plus what will give me the total of 65? That would be 63. Do the same thing with the atomic number. In this case for a neutron it's 0. So 2 times 0 is just 0. So I'm asking myself 0 plus what will give me 30? And the answer to that is 30. All right, so now I have my top number, my mass number is 63, and my bottom number of 30. The last thing I'm going to do then is look on the periodic table. Since this has an atomic number of 30, it's not going to be one of these special particles. I go on my periodic table. I find what has an atomic number of 30. There it is, 30. And I use the symbol zinc to write it down. And that's how I would get this. All right, I hope you found this video helpful. Don't forget to use these particles. Don't forget when you have a coefficient in front that you have to distribute that to the mass and atomic number of that species when you're trying to figure out how much of the mass and atomic number that you have on either side, whether it's the complete side or the side you're looking for to fill in the blank. And if you have any questions, let me know. Have a quality day.